All right, so we're here with 4.3. 4.3 is a really long section, so it's likely going to be more like 2 days of an in-class section. So just know this will be a really long video likely, with a lot to it, but it will be broken up over multiple different days, so you can watch a little bit of it, take a break, and then come back the next day, watch the rest of it. If you need to break it up into 3 sections, that's fine. And I won't assign homework until we're all the way through it in class. So this is a right triangle trig. So first off, let's think back to SOHCAHTOA. When we have a right triangle, we can use SOHCAHTOA in that if this would be our theta, across from our theta angle would be the opposite side. Directly next to would be its adjacent side, and always the hypotenuse, that longest side across from the 90-degree angle. So when we do SOHCAHTOA, remember I taught you the other, not other way, but just a different way of thinking about it. You can line up sine, cosine, tangent, and the saying is Oscar has a hairy old armpit. Um, so that can help you fill out all the different kinds of ways that we're trying to find what sine of theta equals and cosine of theta equals. If SOHCAHTOA makes sense to you, that's fine. Just know that I will set it up like this when I'm explaining it. So again, Oscar has a hairy old armpit. So then obviously all these functions have their reciprocal function. So cosecant would just be that flipped, h over o. Secant again flipped, h over a. Cotangent again flipped, a over o. So if you can find sine, cosine, tangent, flip them for their reciprocal function. So let's put these to use. We want to evaluate for the 6 trig functions the following triangle. So this is a 3, 4, 5 triangle. That's just a Pythagorean triple. If you don't know Pythagorean triples, another way you could have found this was by using the Pythagorean theorem, right? A squared plus b squared equals c squared, and solving for c. You would get that your hypotenuse equals 5. Again, a 3, 4, 5 triangle. So using these pieces of information, for sine, again, Oscar has, so that would be opposite over hypotenuse, OH, right? OH. So it would be 4/5, and that's it, right? So let me fill these off to the side. Oscar has a hairy old armpit. So you can kind of see where I'm getting these from. So now adjacent over hypotenuse. Again, if this is our angle, adjacent would be directly next to, which is 3. And hypotenuse, always longest side across from 90 degrees, is 5. So 3/5 for cosine of theta. Tangent, opposite over adjacent. Opposite is 4. Adjacent is 3. So 4/3 on that one. And keeping it going. For the rest of these, now we're going to take this saying and just flip it. So now this is h over o. So essentially, you don't even have to go back to your triangle. All you have to do is take this triangle and flip it. So 5/4. Take this triangle and flip it. 5/3. Take this triangle, flip it. This fraction, flip it. 3/4. Okay? And again, these are our reciprocal functions. So it's directly over h, now h over o. So we're taking the denominators going on top, numerators going on bottom, so you can literally flip this fraction to go ahead and get this evaluation. Just kind of that easy. So again, if you don't know Pythagorean triples, that's more than okay. You can use the Pythagorean theorem of a squared plus b squared equals c squared to find that our hypotenuse was equal to 5. Okay. So now I'm going to move you on to trig identities. So I will give you a sheet that has all of these on them, but these are really helpful to kind of have written down in a safe spot that you can keep flipping back and forth to. So the first identities are specifically our reciprocal identities. So something that's an identity is something that's true for every single thing in every single situation in math. And specifically identities is where they have multiple representations. So sine truly equals 1 over cosecant, meaning you could replace sine with 1 over cosecant, but this equal sign goes both ways. So you could replace 1 over cosecant with sine of theta. Okay, so identities are something that are always going to be true. As soon as you start getting into calculus, especially, these are going to be things that should just be memorized. They should just kind of be second nature to you. At this point, I will continue kind of letting you start that memorization process, but just know that moving forward into calculus, these will be expected to be memorized. So your reciprocal identities, remember when I was talking before, with reciprocal functions, I said it always goes sine, cosine, tangent. And that's opposite of what you would think. S for sine matches up with C for cosecant. C for cosine matches up with S for secant. And then tangent and cotangent very obviously go hand in hand. So our reciprocal identities takes that reciprocal and simply says, whatever that original function was, put it 1 over its reciprocal function. And that's the identity. Same thing for our other ones. Take its reciprocal, 1 over what its reciprocal would be, and that's the identity. So knowing that sine and cosecant are matched up will help you remember cosine and secant, tangent and cotangent. But really that's as deep as those kind of go for now. But again, I can't stress enough that the reason we use identities is in order to make substitutions. So say I had a sine and I needed to get it in terms of cosecant. I could replace sine with 1 over cosecant. And that's a very fair legal trade in math. You can make that substitution and it's completely mathematically correct. Now we also have what's called our quotient identities. Quotients means basically just division. So these are both our quotient identities deal with tangent and cotangent. Knowing that tangent and cotangent are reciprocal identities, it's not surprising to know that their identities are also reciprocals of each other. So tangent is sine over cosine, whereas cotangent is going to be cosine over sine. So again, taking those reciprocal identity or matching up those reciprocal identities, tangents identity is the reciprocal cotangent's identity. Again, can replace cotangent with this identity, can replace this identity with cotangent. Last but not least for this part of identities is our Pythagorean identities. So the most common one that you'll remember would be, would be sine squared theta plus cosine squared theta equals 1. But we also have 2 more. The next is 1 plus tangent squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. So something that's important to remember about these is you can manipulate these in any way that you need. So say I wanted to have this, and I'll show you the different representations for just this first one. Say we wanted to isolate sine squared. You could write this as sine squared theta equals 1 minus cosine squared theta, right? Because the two of those are equal, I just moved one thing from one side of the equal sign to the other. I could also say cosine squared theta equals 1 minus sine squared theta. Okay, you kind of get the idea. You can manipulate these, you can move things from one side of the equal sign to the other, and they will still be true. Again, you can do that for any of these. So that's the important thing to remember, is that you can manipulate these to do whatever you need it to do. So the reason we're talking about these is I want you to apply these trig identities. Specifically, let's apply them in order to find the value of trig functions. So for this example, we want to let theta be an acute angle such that cosine theta equals 0.8. Okay, knowing that cosine theta equals 0.8, we want to find the value of sine theta and tangent theta using trig identities. So what we have to think about is, if you know what cosine is, what identity can you use to then figure out what sine is? So we want to flip back to all of our trig identities, and you can kind of take a look through these and say, well, what has both sine and cosine, and wish that I could solve for it. Hopefully, one that you're kind of falling down to would be this Pythagorean identity. The reason we cannot use these quotients is because it also involves cotangent and tangent. I would only be filling in my knowledge of cosine, so I'd still have sine and cotangent, or sine and tangent, and I wouldn't be able to specifically solve for sine then. So instead, let's look at our Pythagorean identity. I can solve for sine, filling in my knowledge of what cosine is, right, this identity right here. I can use this one and manipulate it by filling in what I know for cosine. Then my only term that I have not substituted a value for would be sine, so I can then solve for sine. Let's flip back over. If we use the Pythagorean identity, sine squared theta equals 1 minus cosine squared theta. What we want to do is plug in our value for cosine. So we still have sine squared theta equals 1 minus 0.8, but notice that was just our regular cosine. This is a cosine squared. So you then have to say, all right, that's my cosine value. Now I have that cosine value squared. So at this point, you would need to take, let me go find my, oh, I guess I don't really need solving for these. Okay, you won't need a calculator yet, sorry. I thought I was gonna actually truly evaluate a calculator yet, but not quite yet. So yeah, let's keep solving for this. So sine squared theta equals 1 minus 0.8 squared. So you can just think about this as 0.8 times 0.8, which would be 0.64, right? Because 8 times 8 is 64, so just throw that decimal in front of it. Keep solving. Sine squared theta equals, what is, 1 minus 0.64. It's going to be 0.36. Again, all I'm doing here is solving. So remember, we wanted to solve for sine. I currently have sine squared theta value. So to get rid of a square, you have to take the square root, giving us sine of theta equals the square root of 36 would be 6. So it would be 0.6 as that sine value. Now let's find tangent. Let's go back to our fundamental trig identities. We can be looking for something that has tangent and sine, tangent and cosine, or tangent, sine, and cosine. So my reciprocal identities will not help me. My Pythagorean identities don't involve anything with tangent and cosine or sine all in the same identity. So back up to quotient then. Tangent of theta does equal sine theta over cosine theta. So I have my sine and I have my cosine value. So let's use this identity. That it equals sine over cosine. My sine value was 0.6. My cosine value was 0.8. If you divide those, you will be getting 0.75 for your tangent theta. One thing I just do want to point out, if you are going to try to put this into your calculator, let's say you want to know what that value would be, just make sure if you're doing anything with degrees, meaning it's a degree, not a radian, so it doesn't have pi in it, you want to go to mode and put your calculator over into degree. See how I'm flashing over degree right here. You would want to put this in degree mode if you're working with degree. I'm going to put it back into radians because I've been generally working with radians, so I'm going to put it back over there. All right, let's do another example. We now want to let theta be an acute angle where tangent theta equals 3. So using the fact that tangent theta equals 3, we want to find the values of cotangent and secant. So for this example specifically, what I would do is I would go back to my fundamental trig identities. And again, start with, okay, if I have my tangent, how can I find my cotangent? And then if I have my cotangent and my tangent, how can I find my secant? So this would be a great example to go ahead and pause here and try to get as far as you can on this example by yourself. Okay, whether or not you've tried this example, let's go ahead and go through it. So looking back at my trig identities, the first one I'm drawn to right away is the fact that tangent's reciprocal identity is cotangent. I have only tangent and cotangent terms within one single identity, so it seems like the best one to use for me. So I know that cotangent equals 1 over tangent, again, by the reciprocal identity. So knowing my tangent is 3, this would then be 1 over 3, or that cotangent theta equals 1/3. Okay, so some of them truly are as simple and quick as that. Remember, when we were finding our sine value before, we had quite a few steps to go through. This one, it was just a really quick identity. So now we want to say, okay, well, is there anything that has secant in it? Okay, so now we want to find secant that also has an identity with tangent or cotangent or both. So flip back to those trig identities. Try to see what's the one that looks most promising. As I look through these, the one that's sticking out to me the most, the one that can help me find secant, and it's not going to be a trig identity because I don't know cosine. It's not going to be a quotient identity because I know tangent and cotangent, but I don't know sine or cosine. So looking at Pythagorean identities, not the first identity because that has sine and cosine. The second one does have tangent and secant. The third one has cotangent and cosecant. My goal is to find secant, and I do know tangent, so let's use this one. Secant squared equals 1 plus tangent squared. The only thing is now I have to add a squared onto secant, meaning I'm going to have to square root this when I'm done to ensure that I'm finding the actual secant value. So I don't know secant, but I do know tangent, and that is 1/3. And again, it is tangent squared. So I have to put in, oh, sorry, tangent is 3. I was looking at cotangent values. Let's cross that one out. So secant squared theta equals 1 plus tangent is 3, quantity squared. Solving for secant squared right now, 3 squared is going to be 9. 9 plus 1 is 10. So we'll have the secant squared equals 10. Last step is taking the square root to actually find secant itself, giving us secant theta equals the square root of 10. Square root of 10 can't be simplified at all. You'll get a nasty decimal when you plug that in your calculator. But there are our cotangent, we just found our secant, and along with our tangent values. One thing to note, sometimes there are different multiple ways of going about this, but you can still get the same right answer. So you could essentially use a different trig identity in order to solve for these, but as long as you're doing that, using that trig identity in a mathematically correct way, you will get the same correct answer. All right, last couple kinds of things we're going to talk about. Not only do we evaluate and solve for trig identities, but we also verify that statements are true. So I want to be able to verify that the following two statements are true. Let's look at the first one, A, first. And again, we're just verifying the following using trig identities. So this statement is cosine theta times secant theta equals 1. So we have to think, what do we know about cosine and what do we know about secant in order to be able to find a way to prove that the two of those things multiplied together equals 1. And again, you're going to find multiple different ways to be able to go through these as well and still be able to verify them. So the first thing that's standing out to me is that I know that cosecant and secant are reciprocal identities of one another. Being reciprocal identities, that means that cosine has the reciprocal identity of 1 over secant, and secant has the reciprocal identity of 1 over cosine. So if I'm thinking back to some of my trig identities, I'm looking at these reciprocal ones, because these ones are, again, the ones that are standing out most to me. Since cosine equals 1 over secant, you can literally replace cosine with the identity 1 over secant. So when we go ahead and do that, that is saying, okay, it's no longer cosine. I'm replacing this with 1 over secant, there we go, secant theta. And then I'm not going to replace secant theta. I'm just going to go ahead and leave it. And it still is equal to 1. When you have when you have a fraction times a whole number, you multiply the whole number by just the numerator. Meaning now I have secant theta over secant theta equals 1. Secant over secant over secant equals 1. So 1 equals 1. And that one has been verified. Okay. So the hardest part for some people to understand with these is how we're just able to replace things. You truly can use those identities to replace anything that they equal. So they're all interchangeable. Both sides of the equal sign go both ways. I could have replaced secant with 1 over cosine and gotten the same ending example. Some people's routes take forever, but they still get to the same answer. So the more that we practice with these, the more you'll start to realize what to replace with what. So this second one, this is secant theta plus tangent theta times the quantity of secant theta minus tangent theta, all equal to 1. Venti, stop it. Hey, stop. Good boy. Good boy, stop. Okay. So the first thing that I'm that I'm having like an instinct to try to do would just be to FOIL this. Because when I'm looking at my identities, I have secant and tangent in the same Pythagorean identity, but they have to be squared. I don't have any secants or tangents that are squared here, so that's not going to work for me. They are not reciprocal identities of each other, and there's also no quotient identity for either of these. I could replace tangent with a quotient identity, but it wouldn't get me anywhere. So I'm just going to go ahead and try to FOIL these and see where that gets me. So secant times secant squared theta, secant times negative tangent. Negative secant theta, tangent theta. Tangent times secant, positive tangent secant theta, and tangent times negative tangent is a negative tangent squared theta, and still all equal to 1. So we have a positive and negative tangent times secant, meaning those will cancel out, leaving me with secant squared theta minus tangent squared theta equals 1. Let's flip back to a Pythagorean identity, because I remember one having both tangent and secant. So think about a version of this. If I wanted to isolate one, I would have had to subtract over tangent squared, giving me secant minus tangent. I have secant minus tangent equal to 1. That's saying that this chunk right here, the Pythagorean identity, let's go back to that one. The Pythagorean identity right here, if I subtracted this over, again, we have 1 equals secant squared theta minus tangent squared theta. This chunk is equal to 1, meaning all of this can be replaced with 1. That helps us because if we replace this entire chunk with 1, 1 equals 1, and we verified it. One last example, and I would urge you to try this one on your own, but again, I'm getting a little bit more complicated relatively quickly because we're going to do a lot of different practice with these, but I want you to see some easier versions, some middle versions, and then a little bit harder version in your notes so that you can kind of reference back to these to see how we handle them here. So the very last one is cotangent squared theta equals 1 over sine squared theta minus 1. So there's a lot going on here. I like to start sometimes with the more simple version. So starting with this cotangent squared, I want to try to see, is there any way that I could possibly manipulate that side to look like this side? Because essentially what we're doing when we're working with things with verifications with the equal sign, you generally want to only manipulate one side. So I only want to touch this side, or I only want to touch that side. Meaning I want this side to look like that side, or this side to look like that side. But we're never going to like start multiplying and doing all these crazy things. It just gets really complicated really quickly. So I'm feeling like my best bet here would be to start with cotangent squared theta. So in doing so, my first instinct is that if I could use a quotient identity, that would bring up a sign, okay? Because I know my quotient identity involves both cotangent and sine, okay? Yes, I'm also going to bring in a cosine, but I'll deal with that because there's no other identities that involve both cotangent and sine. So my guess is this will help me get somewhere. So since cotangent equals set this over here, since cotangent equals cosine over sine, then cotangent squared equals cosine squared over sine squared. Okay, so that square is just going to end up distributing out just like, right, it's just that addition to that identity. So we're going to replace cotangent with cosine squared theta over sine squared theta, still equal to 1 over sine squared theta minus 1. So now I have this squared in the denominator, but I still don't have the top equal to 1, and I'm still missing the minus 1. So I still have more work to go. I want to get rid of that cosine. I don't know how I'm going to do it, but I do want to get rid of the cosine, or do something with my sine. So I look back at my identities and I just start thinking, well, what right now has a cosine in it that I could help get rid of that cosine? If we look at reciprocal identities, I would just turn it into a secant, or I would just turn it into, down with quotient identities, I would just end up turning that entire thing into back into cotangent, which is not what I want to do. Okay, I just got away from that. So my reciprocal identities won't help me, my quotient identities won't help me anymore. So it's got to be my Pythagorean identities. So the ones that involve sine and cosine is this first one. And I start thinking about, well, cosine squared is equal to 1 minus sine squared. So maybe that could help me. That would at least get me into terms of just sine, which is kind of what I need. So maybe let's do that. Okay, there's no harm in trying things. The biggest thing with these is you have to be willing to try and fail and start back over. So we take cosine and we replace it with 1 minus sine squared theta. Again, that is just a Pythagorean identity, just doing that substitution. It's still over sine squared theta, and still set this equal to 1 over sine squared theta minus 1. So you're not always going to need identities. Sometimes you can use your prior math knowledge and your knowledge about fractions and how you can kind of manipulate things, and instead of doing a substitution, just manipulate what you have instead. So I'm looking at this and I know if I have 1 term in my denominator but 2 in my numerator, I can split this fraction up. I know I have to have this split up by subtraction eventually, so why don't I try splitting this up? Specifically, you can split that first term over the denominator by that second term over the denominator. So it would be 1 over sine squared theta minus, because that's the sign in the middle, sine squared theta over sine squared theta equals 1 minus sine squared theta minus 1. So I'm almost there, right? I have these first terms, 1 over sine squared theta. I have a minus, but these two terms are different. I need to have a minus 1. Sine squared theta over sine squared theta cancels out to just be 1. So eventually, I finally got down to 1 over sine squared theta minus 1 equals 1 over sine squared theta minus 1. And it's been verified. Okay, so that is all that I have for notes for 4.3. Just know that this will be a long lesson in class. We'll take lots of different times with it. We'll take a lot of time working at it. We'll either do some book work or a worksheet, but we're going to try a lot at this. So it's not just going to be dump it on you and kind of keep moving on. This is a really tricky topic, and a lot of people have some difficulties with it. So if you need any help with this, please don't hesitate to reach out. We can Zoom, we can do a Google Meets, we can email back and forth, whatever is more helpful to you. But yes, try your hardest at this. These can be kind of daunting problems and they can be a little bit scary to start, but just know you can fail and then go back up and restart it again. And you'll eventually start to learn paths to take that will more easily get you to an answer. So I've directly guided us toward the right answer with every single one of these problems. But generally, when you're figuring these out, you might have 1, 2, 3, maybe even more trial runs before you finally figure out the right direction to take. It just takes a lot of different practice. So again, reach out to me if you have any questions. Thank you.